You're live now, Zoltan, so you can start.
All right, welcome everyone to this first webinar on exploring multi-domain simulation workflows for sustainable cities and communities, which is a special issue from the Journal of Building Performance Simulation. This webinar series is brought to you by the Educational Committee of IBIPSA, and today we'll have Professor Wang from Concordia University speaking. Before we get there, just a few words on the Educational Committee of IBIPSA. What we do is we identify education and training needs, what we need to do in BPS across all sectors, from academia, private sector, and government. We try to encourage new educational material and methods. We also have training sessions for both members and non-members, and then also, of course, discuss best practices for BPS. And what we do today and in this webinar series is share research results. Everything we do, including today's presentation, is recorded, and you can find it on YouTube after the talk is over, shortly after when we upload it. And in case you missed part of it, you can go and rewatch it and also find all the other ones. And with that, please welcome our speaker, Professor Wang. You can share your screen. I'll stop sharing. And you can begin your presentation. And thanks for waking up so early from us, Professor Wang.
Yes.
Wait.
Good morning.
1 second. Sorry. If you have questions, I'm sorry, I forgot the most important thing. If you do have questions, please put it in the Q&A. And from the Q&A, we will read later afterwards. And then we can ask the questions to our speaker. Now you can take it away.
Yes. Thank you, Lothar. You can see my screen, right?
Yes. Very good.
Good. Yes. Thank you. Good morning. It's early morning for me, but I think probably in Europe it's in the afternoon, right? Good afternoon. I appreciate this opportunity to talk about this recent paper on bridging urban building energy and urban microclimate models. In particular, we are proposing a novel data schema for coupled simulations of these two models. So my name is Leon Wang. I'm a professor and associate director of Center for Zero Energy Building Studies at Concordia University in Canada. So I'll start with the background of this topic, followed by two recent review studies on UBAM and urban microclimate models, and their coupling strategies, and there's different tools for coupling these UBAM and urban microclimate models. After that, I will give you an introduction on CTBS and CTFFD. These are two new models we are collaborating and developing the coupled models. In the meantime, I'll also to give you some updates on recent ongoing projects. In particular, we are working on AI-driven simulations on the urban scale. And lastly, will be conclusions. So this is not a new topic, coupling urban microclimate and building environment simulations. And in particular, in recent years, there's a growing needs of studying the climate change and extreme weather impacts on buildings and communities. So talk about the impact from climate on buildings. There's in terms of the occupant thermal comfort and health. In particular, in recent years, in the events of urban heat island and heat waves. Frequently, you hear from news, there's a reported mortality and fatalities in buildings as a result of heat waves. And in the meantime, there is also concern of environmental pollutions. And in Canada, we have, in the past few years, right, we have a major wildfires. How do we study the wildfire impact on buildings and air quality inside buildings is also ongoing topics. And more importantly, there's a result of these extreme weathers. There's increase of energy demands. In particular, for summertime, there's increasing of cooling demands in buildings. On the other hand, right, there's a building can also affect the urban microclimate, the interactions of and two ways. because of the growing population, we have a built-up area in cities, we are losing natural coverage of the greenery, and then we are also losing natural cooling of plants from the greenery. When building are built really densely in the city, this can also causing reduced wind conditions, creating hotspots and vulnerable regions as a result of heat waves. And more importantly, like in this study, we are studying how the increase anthropogenic heat from buildings, from the waste heat from HVAC system in rooftop units, and that can also create more urban heat island impacts. So basically, how do we study the interaction of both of the topics is an important topic. So what we have done in the literature, right? So this is a recent review we published with Building and Environment, try to understand what has been done to study interaction of microclimate and building environment by using quite a few keywords. As you can see in this slide, the most important study, right, and for urban microclimate is covering about 23% among over 500 papers. Followed this, the second most studied topic is urban heat island, 17%. And very interesting, the study of the urban microclimate, the method has been CFD, computational fluid dynamics. And the method to study the topic, the second method is experiments, including remote sensing and field environments by weather stations. And also some work has been done in wind tunnels in control environments. How about practical issues, right? So UHI is most studied, and climate, outdoor thermal comfort, and building energy demands, and urban vegetations and ventilations, and pollutant dispersions. In terms of the parameters of building have been studied. These are urban geometry like street canyons, building blocks, vegetations, and water bodies and building characteristics, including albedos and green roofs, etc. So what about the study of coupling both domains, urban microclimate and building energy models? This is the second review we have done in 2023, and try to understand what are the state of the art of coupling strategy and different tools. So what we found out, there's quite a few studies already, right? I mentioned it's not a new topic. So for example, there's people have been working on coupling weather research forecasting models with CFD, and coupling Solin with CFD, and CFD with BES, such as NG+, and also CFD with urban climate models, UCM. Although there are different tools, but this has been confirmed, well established. And when we consider urban microclimate or urban climate, there is a more cooling loads predictions in summer, and from 7% to 90% for different cases. And in winter, the trend is reversed. There will be a lower heating loads in winter. So we collect a table of different tools for BEM or UBAM. And probably you all know, well know, right? So this number one most common user tool is NG+, or the urban scale models, CTBS, developed by US Berkeley Lab, Dr. Tianzhen Hong's lab. And there's also other tools, for example, ESPR from Europe, or Transys, eQuest, IES, or CTBEM. That's the in-house model we've been developing since 2017 and 2019, and also Ecotect, and some other commercial tools like Green Building Studio, etc. So the model or tools for urban microclimate modeling, and many architects, they have been using AVIMAT as a commercial tool. Many people have been using it, and there's also the classical CFD tool like Fluent, or open source tool like OpenFOAM. And there's also research tools developed by different universities or labs. For example, UWG, Urban Weather Generator from MIT, or SOTA Microclimate. And also there's tools we are developing for this particular study since 2019, CTFFD, Concordia, in names of CT fast fluid dynamics. So talk about the simulation strategies, right, based on the review. So if we divide all the different studies, we will have three different categories, right? There's a so-called strong coupling, weak coupling, and both of these two types of coupling, they are kind of like two-way interactions. So the output of one model will be input of another model, and then the information will be exchanged in two ways. Or relatively simpler, the so-called normal chaining method. So basically, one model will run first, then the second model will run. The data will be exchanged only one time, one directional. So in terms of the coupling for procedure, right? There's a static coupling or dynamic coupling. So for example, dynamic coupling that can be divided into fully dynamic coupling or quasi-dynamic coupling. Fully dynamic coupling means the information will be changed at each time step. And quasi-dynamic coupling is there's no data exchange at each time step, but it's from different time step to one time step to next time step, so-called the ping pong method. Fully dynamic is like Ani method, what we call, if you use the conventional term. In terms of the coupling, different solvers, the way, right? There's internal coupling or external coupling. For example, external coupling means you run model, you generate the files, one simulations, then the two programs will coupled externally instead of you run dynamically without the user's intervention. So I'll give you a few examples. This is one of the example by coupling AmbiMat and Transys. So first, AmbiMat will run and generate this air temperature, mean radiant temperature, or relative humidity and wind speed. And also, because AmbiMat is known for its capability of modeling trees or greenery, right? It will also provide leaf area densities, temperature, and vapor flux. These will be used for inputs or transit simulations. Then Transys will run and generating from its analysis of mean radiant temperature. Both of these outputs from the software will be used to evaluate or calculate UTCI values for outdoor thermal comfort. The system is run on top of Grasshopper, and it has been demonstrated really successfully to generate some interesting results. The second one is also using AmbiMat, but instead of Transys, they are coupling with NG+. So the idea is similar, which is similar to the previous method. It's like a chaining method, it's one directional coupling. So AmbiMat will generate the temperature, humidity, and wind speed, and then the difference is they evaluate different greenery scenarios. Then they will use this information to simulate a building by NG+, and then we can evaluate the different energy performance and indoor operating temperature. In the end, they come up with the best solutions among all these greenery scenarios. The next one is like two microclimate models. They do downscaling. So one model is so-called WRF, Weather Research Forecasting Model, and they use this information to the model to calculate the time series of temperature, wind speed, and directions, humidity over selected points. Then the information will be used to drive NG+, so that NG+ can run to predict the energy used and take exhaust from the buildings. And then, but the difference is this simulation is dynamic. There are two-way simulations from the WRF and NG+. The last example from literature is Transys with UWG, Urban Weather Generator. It's a model developed by MIT. And the idea of this, the UWG will run and generate or predict the solar, soil air temperature and fictive sky temperature by considering urban heat island. Then the information will be fed into transit simulations so that transit can predict building energy demands and in an urban context. So that's end of the this particular study as a special issue, right? So we are coupling these two simulation models, CTBS and CTFFD, and in a little bit different way. We are proposing a data schema, and which can be generalized for other similar applications. And then we apply these methods for the case of 97 buildings in San Francisco. So talk about these models we are working on since 2019. So this is the model called CD5 Fluid Dynamics model for urban microclimate. It was designed for running on GPU computing based on NVIDIA CUDA infrastructure. So the speed up is achieved by GPU computing and also OpenMP computing on CPU, parallel CPU processors. So the speed up also achieved by semi-Lagrangian methods, basically the new way of solving Navier-Stokes equations of fluid dynamics. Instead of solving all these terms, force, diffusion, advection, or projection altogether, the equation will be solved one by one. We start with the force term, then we solve for diffusion, and then the advection terms are solved by semi-Lagrangian method. And in the end, we are running the projections to achieve the mass balance of different grids. And the simulation is based on larger eddy simulations, simulations. And the unique of these models also, we develop also higher order backward and forward sweeping interpolations to take care of the low accuracy problem when we try to apply semi-Lagrangian method. And to facilitate the simulations of this model, we are also creating a web app, very similar to CTBS web app. And you're welcome to test this app. This web platform has been there for a few years, and so you're welcome to test it. And basically, if you scan this QR code, you probably can even open on your cell phone. So on behalf of Dr. Hong, and this is like short introduction of their model CTBS. So City Buildings Energy and Sustainability, CTBS, is the multi-scale modeling and analysis tool to support cities' buildings, energy, and environmental goals analysis. So it has been applied by many stakeholders and laboratories worldwide for energy benchmarking, analyzing net zero energy buildings or net zero carbon buildings and communities for energy retrofits, renewable energies, or electrification on the community or urban scale, integrating with grid, for example. So there's a lot of interesting applications already in the publications. I think Dr. Hong's website provides a long list of publications by using CTBS. And we are collaborating with him since 2019 and trying to understand the two-way interaction of CTBS and CTFFD and study the heat resilience modeling for San Francisco. So I also put a QR code. You're welcome to take a look at their website and learn more about their model. So short also framework of their CTBS workflow, right? So basically the workflow including the data inputs, including weather data, building stock, footprints, and land uses, and also databases, for example, utility rates, codes, and ECMs. Then after that, there's a simulation engine based on NG+. So the idea is when we apply or extend NG+ on the urban scale, each building will generate one NG+ input. And then by batch processing and simulations, the model is able to run on the community and urban scale. And the visualization is also achieved on the same platform. It's really interactive and interesting platform. You're welcome to test it. So back to this particular study, right? So basically, because when we talk about the different models, UBAM on the urban scale and also Microclimate, there's an inconsistency of these different scales in space and time. For example, and each building on the nodes, the surface node on building envelope, so-called red nodes, can have different nearby air nodes with so-called blue nodes. And one red node, as you can see from this picture, may have multiple red nodes in the safety domain. This picture shows one red node A can have multiple 9 nodes or air nodes. And similarly, one blue node on this picture shows on the left, one can have multiple surface red nodes, right? So how do we bridge the spatial difference? This really creates a challenging question. When we developing coupling strategy, right? So we talk about there are certain criteria we have to follow. Basically, the idea is we need to make sure each red node and blue nodes, there's one-to-one connection. And the second concept important is we need to avoid the double counting. So we need to make sure the heat flux from one surface node of the red won't be double counted when it's applied to the blue nodes on the microclimate side. So these are some of the challenges we are facing. And in the meantime, the data exchange between two models, right? Because of the it can have multiple parameters. So for now, we are exchanging wind speed and temperature plus wind direction from the UCM. From building side, we are exchanging heat flux and temperature from building surfaces, so that we can evaluate, right? So what will be the amount of heat, waste heat generating from buildings to the environment, and now see how the two-way interaction of increase in temperature of the surrounding air may affect the cooling energy usage of the building on the larger scale. And another challenge we're facing is some of the information will be static, and some of the information will be exchanged on the run, right, dynamically. So the static information, right, we call the we are using a JSON format, right? For static information, you can see in red, highlighted in red here, including the UCM static JSON files covering different air locations, their indices. There's also static information from building UBAM, and including surface IDs, their names, and there's also static mapping, right? As I mentioned, red and blue nodes mapping. Those are constant information that won't change during the coupling process. In terms of dynamic JSON, this is a second set of files created during each iteration step. So for example, as I already mentioned, so we are exchanging both ways from the UBAM, we are exchanging heat flux and the temperature of surfaces. From the UCM, right? CTFD, we're generating wind speed and the temperature plus the and wind directions. And another difference compared to conventional method, because we are not talking about just one single building or a few buildings. We're talking about we run multiple buildings, even on urban scale, and for a long time. So what we are proposing here, instead of interaction and exchange data at each hour, we run CTBES first for 48 hours. We get all the results, and we run CTFD for 2 days by using the information heat emissions from CTBS. Then we generate all the results. Then we repeat the whole process So the interactions only occurs for 48-hour simulation from both models. Then when do we stop the interaction? So the interaction stop criteria, we set the T surface temperature of the temperature of all the surfaces when it's less than 0.3, we think this already converged for the coupling. So to apply this study, we select the one of historical heat waves in San Francisco, 2019. So in that year, there's a record-breaking temperature in downtown San Francisco, 41 degrees. And there's also 14 people reported dead and hundreds were sent to hospital. And also, I mean, this is a growing trend, right? And also in 2024, heat wave, the temperature again reached close to 34 degrees Celsius. And so what we do is, as the first study, instead of working on the whole city, and we select a community with 97 buildings. So the climate of San Francisco is climate marine type, climate zone 3C. And we did 48-hour simulations for this September 1st and the 2nd, 2017. In terms of the urban scale simulations using CFD, right, we are creating a domain size for 1 kilometer, a close 1 kilometer with height of 350 meter. This total of this case is 35 million grains. Here are the results. So basically, the figure on the top right shows the predicted temperature of the converged simulations. And by the way, the coupling was found to be converged after 3 rounds of the data exchange. So we started CTPS first, then we end up with a 3rd round of the coupling of these 2 models. So as you can see, the predicted temperature, right? The building average, the building surface temperature of one selected building after the 3rd round of simulations, the temperature difference compared to the round 2 is less than 0.3 degree. And also based on the results, during the daytime, in particular around 2 p.m. of these simulations, the temperature of the surface for this office can reach up to 55 degrees. And the predicted air temperature for this study also demonstrate this figure shows that the first grade temperature is found to be around 50 degrees of that. So basically the building surface temperature is found to be higher than the air low temperature for the first grade of CFD simulations. So as a result, right, there's an increasing amount of heat emission from buildings as a result of the running of HVAC system or air AC system in different buildings. So the hourly peak of the heat emissions was observed around 2 in the afternoon, right, to 4 p.m. for this building. And also interestingly at night, right, because temperature of the air can drop, right, to below 25, 22 degrees. So some even, I think the building is running probably on the natural cooling mode. These are also, the heat can be also negative. Basically the air help to cool down the building at night. But at daytime, there's an increasing amount of heat emissions from the building because of the AC running of the systems. So if you look at also predict the air temperature at the 5 meter for different times of the study, right? So 6 a.m. morning, noon, afternoon, and night. So this shows the air temperature, ambient air temperature for these 97 buildings community. So for example, at the mornings, right, the temperature can around on average about 20 degrees. And then at noon and also afternoon, some of hotspots is observed the temperature can reach like around more than 50 degrees for this particular day. So during the midnight, the temperature drops, right, to although it's still higher than early morning, it's around 30 degree even at midnight. So if we compare the impact of taking into account our microclimate with or without it, right? So the impact on the hourly cooling energy use. So this shows the results of the averaged, if you average all the 97 buildings, the hourly cooling loads in watts per square meter. So what do we see here, right? So basically, if we only use the weather station data for this case, particular day, and then all the simulations have been underestimated. So by taking into account local microclimate, we can see that, right? Because we're taking in account of the double, the increasing heat emission from buildings, then we can see there's around of particular around the 2 p.m. The difference can be around 90% increasing if we consider local microclimate. And then also, we also found that, right? So there's about 5 degree difference. So the for building surface temperature, if we only use the TMY or local weather stations, the temperature is lower than if we consider CFD, which is 5 degree lower for building surface predictions. So there's some ongoing work. After we finish the collaboration for this paper, well, the collaboration is still ongoing. The plan is if we can do a larger case, consider, right, how we leverage the HPC computing power. So that's why we are still developing this version 2. And instead of running on single GPU, we are working on multiple GPU versions. We are aiming for CTFFD at 2.0. So the idea is by using MPI and CUDA multi-GPU infrastructure, and then we trying to develop a multi-GPU version. So we have demonstrated this model for 130 million grids. We showed like a really highly scalability around 97%. And this was kind of like a recent work, right? This is again in San Francisco. The previous case is 97 building cases. Now we're trying to work also on larger 10-kilometer cases, right? So basically, this is the whole San Francisco area, about 140, close to 150,000 buildings for over 300 million cells. By using this new version, we're able to achieve running on 3 GPUs. We can, calculate the result. This shows the temperature distributions and velocity distribution for the whole city. So next idea, the plan is we'll see if we can couple for the whole city with CTBS. So there's also some ongoing work for this AI-driven work, right? Because by generating the data from CTFFD, we're able to explore if we can generate AI models. So this is where we are preparing a paper and drafted. So this is so-called fast localized urban microclimate emulator, FLUME. And basically, we select the 30 cases worldwide based on the urban morphology parameters. Then we train the model for 24 cases, and we demonstrate and test the model for 6 cities. Then we also did something like, because of the model is trained on patches to take care of the lack of data. Basically, for each city, we divided into multiple small patches, small regions. Now we train a model data by using Fourier neural operator, and which is localized for small patches. Then we get result from each patch. Then we merge or stitch each patch together for the whole city. Because it's patch based, then we are able to extend the models to larger cases. For example, we did although it's trained by 1 kilometer, then we are able to predict also the results on 3 kilometer by 3 kilometer cases. And this shows some of the results for unseen city, which is 3 kilometer by 3 kilometer region. And we showed like really nice performance. So this table shows the MAE error is less than 0.3 meter per second for UVW components, and also temperature less than 0.2 degree. So these are what we get some exciting work right on this. So we can generalize the model for unseen configuration from this model, and the prediction accuracy is close to even for wind tunnel experiments. We also demonstrate and predict uncertainties, and then basically for instead of running hours, right, by fitting the base model, we demonstrate that the simulation can be done in seconds and minutes. So conclusions from this paper, this work, right? So we are developing a flexible and general purpose of JSON schema, and then you may apply for your own application of UBAM and UCM integrations. We established a workflow to support both of static mapping and dynamic code simulations running in the batch way, right? So we run 24 or 48 hours one by one, and then we do integration. We also demonstrate this model for 97 buildings, and we're continue working on larger cases. The also simulation shows that the importance of copying by considering microclimate, right? The 20% of cooling load estimated by UBAM alone. So we would like to acknowledge the financial support from NSERC of Canada through discovery grants, and also the recent project we are leading, and in collaboration also with Berkeley Lab, they are a collaborator, transforming building and developing microclimate, advancing resilient science for vulnerable population in decarbonized electrified Canada. This is 5 years projects around 4.5 million funding for this research. So I also appreciate the support and co-author and collaboration from the Berkeley Lab, Dr. Na Luo, and also Dao Tianzhenhong's team, and also my PhD student, Dongxu Zhan, and has been working on this topic. So also, if you're interested in the recent work from our team, and you're welcome to scan this QR code, which is my Google Scholar. You can follow up on our recent work on AI-driven microclimate and other interesting work from our team. So I think I finished the presentation. I appreciate also Dr. Zoltan's invite, and also Pamela's invite organizing this event. Thank you very much.
Thank you. Thank you, Leon. I enjoyed this presentation a lot. Very impressive work. For those with questions, please put them in the Q&A. There are a few queued up already, so we'll go through them one by one. And if you have some that come up later, feel free to email Dr. Wang. I'm sure they'll happy to answer. So the first question by Marjorie Musey, could you tell us why you choose the 48 hours period for the iterations that you have in the coupling?
Well, there's quite a few reasons, right? So 48 hours, these are the heat wave take more than that, but 48 hours because of the computing cost. Because of each hour we run even for 97 buildings or larger cases. And we started with trying to model the whole city, but in the end we found that this too computing intensive, and in particular for the CFD side. That's why one of the reasons. Another reason we picked these 2 days is the worst of the 2 days during the heat wave. I think that's the reason. But now we are talking about if you have multi GPUs, we may extend to longer and also larger cases.
And maybe this answered the question I had, is because you started talking about scaling to the whole city, and so what is the biggest challenge if you were to scale it to the whole, I saw the CFD models, but what about the BS models? And then
Right.
it's a
When we
realistic
come
scale.
to the whole city, right? So I think not many models is able to model the whole city. Some of the simple tools like AmiMap is a little fast, but is limited by computing resources. So we model the whole city. I think again is the challenge of the computing cost. And the another thing is when we extend to the whole city is the validation, right? So what will be the data available so that we can confirm the simulation results, right? So we have a smaller region like 97 building because there's a nearby weather stations. We may validate that. But if we go to the whole city on the CFD level, how do you validate the airflows and all the air the data? So I think if we can take care of the computing first, we can do the whole city. That's the first question. Then we need to find data on the urban scale, not a few weather stations, but more urban data so we can validate the results.
Yeah.
I think also this is what we work with Dr. Hong's team because when they even expand to the whole city, their computing time is also increasing. And like CTBS is running on multiple NG plus files. Like you have 150,000 buildings, like 150,000 NG plus files, right? So a lot of like processing and to be done. And again, by the way, there's also many files exchange, right? There's many static and dynamic JSON files. So basically, but again, I mean, it will be really exciting because of, urban heat island is not a one region urban heat island. We talk about the whole city, right? So to talk about physics, we indeed, I think there's a need. We have to consider the whole region.
Yeah, thank you. There are quite a few more questions in the Q&A, so let me go through those. So first one here is, are there any references or publications that discuss the exchange mechanism between the surface nodes and the air nodes?
Yes, that's this seminar spot, right? So about this paper, I can go that slide. Here. So this is the paper.
Yep.
As a part of the special issue, right? So we provide a lot of details. So if you have your own UBAM or UCM models, you can just use this schema. And it was really with a lot of details, you can just apply a similar method.
Okay, thank you for that. The next question is about the building energy models, I think. So can you, or have you looked into it with Dr. Hong's team also? Can you look at the indoor temperature during the heat wave and how that changes? Like you showed outdoor temperature, it's different. Do you know what happens inside the buildings?
Well, basically, this is during heat wave, right? So most of the buildings are not free running. They are like AC. So this is like may have fluctuations, but they have follow the set temperature.
Right.
But we can report those because of each of the building, there are energy plus simulations. It's multiple thermal zones, etc. So but with AC. So basically, we are integration take care of the heat dump right from AC to the environment in terms of heat flux.
Yeah, I think yeah, I mean
And most of them are rooftop units, for ACs. Maybe some of buildings they don't have AC. I believe they have AC. Most of them. So yeah.
But even
so
with ACs, if your AC is undersized or not, or the heat wave is very strong, you will still not maybe reach the set points, right? So that I think that's
yes,
the next
that's
question.
true. Yes. Well,
okay.
we can look into those, but because of the focus of interactions of this, and and then we haven't looked into the details for. Or when you have more buildings, it will be kind of like difficult to evaluate one by one, right? But we can report that. That will be something interesting. Yes.
No, I think it's very interesting. I think there's a lot of interest in looking at what happens, when you have a heat wave and the power goes out, for example. So I mean, even though you have a
Exactly.
state where there's no power, then a better analysis on the passive mechanisms that either prevent or exacerbate the heating is actually quite important. So fascinating
Yeah.
from that perspective.
Mm.
There's a question on the weather stations. You talked a little bit about it. So sometimes they're far away from the city, or from where your study area is, and that's not the case for you. But what if it was farther away, like for other places, if people wanted to replicate your work with weather stations that are farther away? What is the challenge or other alternatives that you see?
Mm. Well, for this case, we have a nearby weather station, right? So we are lucky. And many cases, because we also simulated Montreal, and actually we also did the whole city.
Mhm.
And in Montreal, we have the data, public data available only, probably only available for three weather stations. But in downtown, we have one at the McGill campus, which is like well, 1 kilometer away. So
Mhm.
basically, if you, that's why I mentioned, right? So that's there's a major lack of the data on the urban data for air, for the
Mhm.
air, for air properties. The surface of the if you want to validate, right? You can validate by remote sensing, like that we are doing now is you can have the satellite the remote sensing data at the fine resolution can be 30 meter, and
Mhm.
you can use that to validate for surface temperature, uh, for skin temperature,
Yeah.
and for air temperature you have to use weather stations. But again, it's better. I would say it's better than nothing. But again, we need more data
Yeah.
for the air. And we did also a recent. Also, you can follow my Google. So we also did a project recently for Health Canada. So that's a literature review study covering different techniques or data available for mapping air temperature and surface temperature or skin temperature of the city.
Mhm.
We evaluate remote sensing, we evaluate weather stations in terms of data available, different methods, and the resolutions from different studies.
Mhm.
And we are generating a report. So you're welcome to look into those. So I'm saying is most of the air temperature, air properties, you can use weather stations or you can use coarser resolution model, like using numerical, like from WAF. If you want to do certain level of cross comparison, that's
Yeah.
another way. But this is information available from the report we have done for this project, the other project.
Cool. Cool. Yeah. Well, so many questions. I'm trying to read. So another question is, so how to get the tree and the water impact on the latent heat flux across the day and night, as inputs to your microscale models with the CFD? Do you use that or not?
In
Oh,
tree, the
yeah, the tree and water impact for
well, I
the,
mean the model like we so the model cannot do the tree for now. We haven't. I mean that's why a lot of people use the element, but
Mhm.
that's the plan next. So we are still working on speeding this simulation up using multi GPU, right? So, but adding trees and consider uh, the uh, the tree impacts, right? And then that's will be our next work. But
Mhm.
this model, we also have we are able to consider shading though. So there's a recent paper we just completed, so that we have building, the shading can be also added to this model.
Okay. Very nice. So there's a couple of questions on computing.
Mm.
I'll read them together and you can maybe answer them together. So, considering the
Yeah.
high computing demand of the tools, do you have any insights on the trade-offs between, detail and accuracy? So that kind of like the trade-offs you're running. And then similarly, because you have, do you have an idea after basically of high performance computing? Do you go into quantum computing? Will that help with your method? So some ideas on the computational costs and trade-offs you have.
Well, always there's a balance or so-called trade-off of accuracy and cost.
Yeah.
So what we are doing here is trying to explore, right? And because if you don't do it, then you don't know how important for example, the climate aspects. So we are able to demonstrate if you consider microclimate, local climate, there's a 20% at least. And some of study they reported 90% I show you in the literature. So, but again, if you want to, it's based on different applications. If you are only do a initial conceptual design, you may not. But if you do like really consider the autothermal comfort or mortality as a result of urban heat island or heat wave, because of the difference of 1 degree or 2 degree, right? That's small, but it has been confirmed, right? Create a lot, major impact on heat vulnerability, right? So I think if you talk about that applications, we do need to take into account of the microclimate because that's in 1 to 2 degree difference. And
Right.
also UHI, we talk about UHI also reported, it has been reported that the UHI impacts most of the in the literature is compared urban and rural, right? So it's about 2 to 3 or even higher. So 2 to 3 degrees has been observed, believed to be a high UHI impacts. So it's all depends on the applications. But if you want to sizing, I mean, engineering for a single building, you can just add a safety factor. But
Yeah.
talk about larger scale and UHI and health related, the higher accuracy will be required. Yes.
So do you think quantum computing will replace the high performance computing?
Yes. So we did a paper. We just because we are also working on quantum computing, and actually we get some good results. But we are not using the quantum computing is like for now it's only at early stage. So they are actually limited by computing resources. So that's why we have this paper. We talk about the BITE criteria. So it cannot deal with data intensive applications. It can only deal with a small problem, but you have multiple possibilities. Like say you have, like small problem, the data is not many, but you have like 10 million or 100 million options for optimization. Okay, so for tiny problem, but large search domain for the moment. So probably in the future, when you have more powerful quantum computer, which is probably similar to NVIDIA, the GPU cards, probably can deal with data intensive cases. But for now, these only for large search optimization problem, not for data intensive applications.
Yeah. Thank you. So I have a few more questions. So I'll ask you for short answers because we're running short on time.
Yes.
One also technical question is the effect of the boundary condition. So if you want to study a smaller district you can be a radius of 1 kilometer, but a 10 by 10 boundary. And when can you say that the results are close to the 10 by 10 grid? Like what's the impact of basically a boundary condition in your
Right. Well, I think he's talking about you have a smaller region, how that, right? Like this case, right? So we only select 97 and smaller region compared to larger. So if you are from wind engineering, there's already established the criteria, right? How do you select the region and how do you set boundary conditions based on what we call local exposure. So basically the wind profile, right, will be different for the local community. And in fact, like if you want to model the 97 buildings, that's why we're following the established criteria, like from the cost or from the, there's a criteria for that. And if, I will be happy to share with more information if you want to know how to set the correct boundary condition for the perspective of wind engineering. Yes.
Cool. Yeah, people can get in touch with you.
Yes.
There's another set of two questions here that are similar, so I'll group them together. They're concerning about coupling back from the building to the environment. The first one was very general, like do you consider or how do you think is it possible to consider, the heat that the building's releasing back to couple it into the UHI effect, so the way back. And then the other one is more from specifically on the schema. How easy would it be to extend the schema from CTBS to more detailed models if you wanted to also simulate not only surface models, but surface temperatures and heat fluxes, but also, things related to ventilation or humidity or more detailed facade scale boundary conditions. So the other direction, basically.
Right. I can answer the schema question first. So
Mhm.
basically, uh, that's why we're developing the schema and when we are both of the developer of these two programs, right? So basically, if you're not a developer, you just do an external coupling. You can just use schema directly. And the idea is if we generate a schema, say from CTFD, and the data will be saved on the file, you have your own UBAM model, and then you can just write your UBAM and read this file. That's why we do schema, right? So this is one application. Well, if you are a developer, not only a user, and then you have your own source code, you can also modify the schema, adapt it to your own application. You're adding more parameters, no problem. So I think this is the two ways of doing this, at least. And so what is the first question?
The first question was about how is it possible to consider the heat released by the building as input
Oh,
to the UHI?
yes. So as I mentioned, the schema will have heat flux and temperature. So those are parameters from UBAM side. And then when you apply this to, you can use a heat source directly for the local for cell, no problem. Or because if you only use, what we do is, what in the coding is with the heat flux and also temperature, we change the local heat transfer coefficient. So there's multiple ways, but as long as you need to make sure that the total heat from the building is counted,
Mhm.
it's not double counted and counted enough. And I think that's a solution. Yes.
Cool. And then the last question, thank you. You see, it generates a lot of questions and ideas. It's great. Last question is more about the goal here. So what's the point of simulating a whole city? Wouldn't a neighborhood scale would be, better because it's easier to do and it's more accurate and maybe better reliable
Yes.
results. So what's the point
Well,
of a city?
yeah, I think the same. Thanks for the question, right? So the same concept is in the beginning, people because of limited computing, they just like resources, they just do one building, right? One
Mhm.
building. Then you have CFD. But now we go to the community. Now I have to go to urban. Why? Because of there's a nearby impacts, right?
Mhm.
So we talk about in terms of urban heat island, right? It's an urban heat island. It's island. It's not one building, right? So we need to go to the whole city. Then we identify the needs for the whole city, right? For the urban heat and impacts. Then we'll say, oh, maybe for the particular cases, you can will be enough just do a small community because the nearby impact is low, right? Or you
Mhm.
can go to a single building because the nearby is far away from other buildings or with the neighborhood is not important. I think, and I'm from research side, we need to generate this is some new research direction. We need to generate some of the guidelines, criteria, right? So to the size of in terms of space and the time, right? Why 48 hours? Why 97 building? Why the whole city? I think
Right.
this need to be evaluated. This will be something interesting, but we have to do this whole city first.
Yep. Thank you, Leon.
Yes.
It was very, very informative and very interesting. If you could let me, so thank you for presenting. I think everybody thanks you because you can hear you, but there's standing
Oh,
ovations in the background. So
okay.
thanks everybody for attending. I will just share a few more thoughts on the next event. I hope you can see my slides. So this is what we had earlier. In this seminar series, we'll talk also about EVs and digital twinning and emission pathways. And then the last event with Clarice, Lori, and Camilla are about the whole special issue or discussion around that. So please sign up, send us a note if you can't find the links. And very briefly, next week, there's a last webinar of the Baptist series. You probably see some announcement. If you're not, you can take a note on the date. And with that, because we're on time, if you want to support the BIPSA, the price is there without the impact on fossil fuel that you had recently. So with that, thanks you everyone. And we'll see you at the next event, which will be Monday, 11th May in this webinar series. Thank you. And thank you again, Leon, for sharing your thoughts.
Thank you. Thank you very much.
Thank you all.
Thank you.